Activity, we saw some strings, varying Lagrangians, how to put boundary conditions. We learned how to put boundary conditions that lead to D-branes. We understood the Nambu-Goto action, its properties, its sign, the reparameterization invariant, why that constant in front is called the tension. We also learned how to use the reparameterization invariance to simplify the problem of finding solutions. That was really applied general relativity in 2 dimensions. The idea that, well, you have this symmetry, you change coordinates and nothing changes, but this time you had to change coordinates and find very special coordinates to have any hope of solving the equations. And that worked out quite well. We solved the equations. There was something about those equations that maybe didn't strike you as so terrible. Well, certainly were wave equations, that was okay. There were boundary conditions that at the end of the day, this P sigma was the thing that must vanish at the endpoints of the string to have a free string. And that was not bad. The thing that is difficult, in a sense, are these Virasoro constraints. Now, it didn't cause much trouble because we didn't try to find very general solutions. The idea was, at the end of the day, you had this function f. So I'm just reviewing a little what was going on that had to do with the motion. The x of t and sigma was related to f. And this f function vector had to have unit length, and that's a complicated condition. Basically, if you parameterize f, if you say it's f as a function of u is some sort of length parameter along a curve called f. It's a nonlinear condition still. You know, it's not linear wave equations. So, in a sense, finding very general solutions of the equations of motion of a string, even though it's very manageable, and now you can do it with a computer, and you can play with many examples. They're at the end of the book, and I think you may have something to do in the homework with that. You're far from being able to write absolutely general solutions. So today we're going to take the steps that are going to allow us to find the most general solution of the motion of an open string. And a solution without a constraint. At the moment you're done, there's no constraint to be solved, nothing like that. And that will be through the use of the light cone gauge. This light cone gauge, again, is one of those things that you hear about, and you know, well, the light cone, degrees of freedom on the light cone, all these things. But suddenly, the fact that using the light cone gauge, you can solve an equation that you couldn't solve otherwise, it's a very unusual thing. And it's the only way the string was quantized for the first time. Nobody could quantize it any other way than in the light cone. And in fact, it's the way we use it nowadays to quantize it, the way you learn it, and eventually you get what is called covariant quantization of the string, which is a lot more abstract, more powerful, and more general, but less intuitive. And if you want to know what are the degrees of freedom of a string, you go to the light cone, and you always see that. So let's begin by going back to a thing that has been showing up forever now. So we have these symbols, p tau mu and p sigma mu. And that was dl, the x dot mu, and dl, the x prime mu, and they were very crucial for all our analysis. So what are they, really? What are these things? Apart from being defined this way, and what did we learn from them? We learned several things already. We learned that this one, P sigma, was the one that had to be put to 0 at the end of an open string if you had a Neumann boundary condition, if you wanted to be free. And if it was fixed, well, you certainly can say that x has a particular value at the end of the open string, and you're okay. So what are these? And what we're going to learn is that this tau and sigma, they were not just labels, but in fact, they were indices, and these are currents on the worldsheet. Conserved currents on the worldsheet, moreover. Conserved currents in the two-dimensional sense, in the two-dimensional world. So let me remind you of a little theorem that you have for Noether currents. So if you have a Lagrangian density L, fields phi A of some coordinates psi, and I will label the coordinates psi alpha, with alpha from 0 up to some number d. So if you have a Lagrangian like that, and symmetries, or symmetry transformations, delta phi A, so you change the field, symmetries, delta phi A, you change the field, leading to delta L equals 0. That's a narrow definition of a symmetry. If it leaves a Lagrangian invariant, it's called a symmetry. You probably know quite well that you can leave it invariant up to a total derivative and you still have a symmetry, but we don't need that much today. Suppose it just leaves it invariant, the symmetry. Symmetries with parameters epsilon I, that may sound a little funny, but you have a symmetry. To every symmetry transformation, you associate a parameter, and you may have several symmetries. So let me call the parameters epsilon I. It's a different index because the I labels the different symmetries. The alpha, the different coordinates, and the A, the different fields. So keep track of 3 indices are being introduced here. Alpha, A, and I. Then we have currents, and here is the name of the currents, Ji alpha, that are conserved. So let's see what this means. Well, first the definition of the currents, and here's the index I. There is a current for each parameter in the symmetries. So if you have a parameter, independent parameter of the symmetry, there's a current for each parameter, because if you had a single symmetry, epsilon, well, there would be one current. So what is the formula for this current? Ei J alpha I of psi, because it's a current that lives on the world where this Lagrangian lives, is dl d partial d alpha phi A delta phi A. That's the most familiar version of Noether's theorem. That's how you compute a current. And these epsilons eventually are supposed to cancel because they are part of the definition of the variations, as we will see. And what does it, here is the definition of a current, and what about it? Well, it is conserved. So d psi alpha of J alpha I is equal to 0. That means conserved. It's the analog of what in field theory you typically say d mu J mu is equal to 0. And you realize again that this I is an index for the different currents. It has nothing to do with the conservation. It's just the different one. So there are as many equations here as there are values of I. The alphas are summed, as always. And finally, if you have a conserved current, the most immediate use of a conserved current is having a conserved charge, which you know what charge is in electrodynamics, is the zeroth component of the current. The spatial components of the current are the currents. So this current, this Lorentz vector that is a current, the zero component is the charge density, and therefore the charge is given as an integral over space, so over d psi 1 up to d psi d of the charge density, which is J0 of psi, and the I goes for the ride. There's I currents, I charges, and they are conserved. Now, what does it mean that they are conserved? It means that the time derivative of this quantity is 0, and that's a calculation that probably rings a bell. You take the time derivative here, you get into here, you get the time derivative here, and then d0 j0 is equal to di ji, and that's a total derivative in space. And if the fields or the currents or things are fine at infinity, you get a conservation. So this thing is conserved if the total derivatives that appear here are 0. So this has d psi 0 of qi is equal to 0 with good boundary conditions. So this is a field theory result. This probably is something you've seen in your field theory course. Did you see this theorem? It looks good. So the only thing we have to do now is to apply it for the string. And for us, let's see what we have. We have a Lagrangian that depends on x dot and x prime. The coordinates for us, psi alpha, are tau and sigma. And what is a symmetry? What symmetry do we have? Well, there's one symmetry that is always present when your Lagrangian just depends on derivatives. You can change the field by a constant. Here, what are the fields? What are the phi a here? The phi a here are really the x mu's. These are your dynamical variables. Phi a's are the x mu's. Psi alphas are this. And what is there that is a symmetry here? Delta x mu equal a constant, epsilon mu, constant. Since this Lagrangian just depends on the derivatives, this transformation, if you change the delta x by a mu, this x dot doesn't change, x prime doesn't change, the Lagrangian doesn't change, you got a symmetry. And this is a very important symmetry. It's a symmetry you know very well. It's translational invariance. The dynamics of the string doesn't depend if you do it here in this room or in the next room. You can do a constant translation. You can do it today or tomorrow, and it doesn't matter. Translational invariance, part of the Poincare symmetry. So what are the currents associated to this symmetry? Well, we can go and use this formula. And what do we have? So here is this formula, but we can continue. So let's look at this formula. Epsilon mu, the index mu is played by I here. So we'll put epsilon mu, j mu alpha. And it's very tempting to think that this is the index for the current, because you always see d mu, j mu. But no, this is just like a label now. It's the different currents. There's different parameters, different currents. There are going to be lots of conserved currents. and this is the index of the conservation. So this would be dl, d alpha of the field, but the field is the x's. So this is with respect to x mu, and here I should put delta of x mu, this formula. But this, well, it's not that difficult. This is dl, d alpha x mu, and delta x mu is epsilon mu. So epsilon mu times this is epsilon mu times that, so j alpha mu is nothing else than dl d alpha x mu. And as you can imagine, j mu 0 is equal to dl d0 of x mu, which is dx mu dot. And that's our p mu tau. Similarly, I'll write it here, but j mu 1 is dl with respect to d1 of x, but d1 of x is d sigma, so that's x mu prime, which is p mu sigma. So indeed, like tau and sigma, these were just indices of a current. It was a good notation in the sense that even though you thought it was just reminding you perhaps of the parameter tau, is the zero index of a current. Now, once we've identified them, remember that we had an equation of motion. But what can we say here? J mu 0, it is a conserved current, so d0 j mu 0, d1 j mu 1 is equal to 0, which is dd tau of p mu tau plus dd sigma of p mu sigma equals 0, and this was the equation of motion. So the current conservation, in fact, is our equation of motion, and that is fine. That's what happens with sort of free objects when you have this kind of momentum conservation. Okay, questions so far? Anything about these indices or application of the Noether theorem that is confusing? Daniel. Sorry, this quantity is conserved. Well, we're going to talk about this. In fact, this is a good question. What kind of conservation is this? So let me write the conservation first. So what are the conserved quantities? Well, I could call them currents sub mu, because the index I for the various epsilons is a mu index, but I will actually change the name. I will call them P mu. Why? Because these are conserved currents associated with translation, and those are momenta. We call momenta the conserved quantity associated with translations. So there's P mu. Let's put a tau here, although it's presumably not there. It's going to be the integral over what? Over space. Space in the world where these things live is sigma. The sigma from 0 to sigma 1 of P mu tau. Of tau and sigma. That should be our conserved quantity. Let's check that. We would have dp mu of tau d tau is equal integral d sigma of dd tau of p mu tau and that's 0 to sigma 1 integral d sigma by the equation of motion is minus dp sigma mu d sigma, and therefore this is minus p mu sigma evaluated between sigma 1 and 0. So indeed, you know, what is supposed to be conserved in the sense of what the symmetry guarantees is that up to total derivatives, things should go fine. If you put the right boundary conditions, remember free boundary conditions meant this p was 0. And if that p is 0, it's free, and therefore the momentum is conserved in that direction. If you have a string between two d-branes and you have them over here stretched, it can move freely in this direction, the whole string, and that direction of momentum should be conserved. On the other hand, if you hold the string here and it's vibrating up and down, it's holding it, so it cannot move up and down the endpoints, then the momentum in that direction is not conserved. Sometimes the whole string is going down, sometimes it's going up. So this makes absolutely good sense. You pretty much get the conservation, but if and only if you've put these free boundary conditions around the directions that you want it to be conserved. Let's assume if those vanish, if p sigma mu at these endpoints are really 0, then you get dp mu d tau equals 0. It's independent. And we say it's conserved. But then that's a satisfying statement, but then it's a little confusing. ddp tau is equal to 0. Wasn't it supposed to be conserved in time? Now we got conserved in tau. What are we supposed to do about that? And that's a general thing that happens in string theory, in membrane theory, in all these theories. The symmetries are symmetries on the world that is the string, and you're going to get conservations in that world, not in your world. You're watching that string and you say ddp tau, I wanted ddpt, ddt. I wanted as time goes by, this momentum is conserved. But you didn't get that. You got this. So there's a discussion that should be made here as to why these conservations make sense. Now, if you're practical, you could say, use the static gauge, come on. Static gauge T is equal to tau, that's it. It's conserved in time. And actually, you know, it's not a bad argument. It is correct. You trust your reparameterization invariance. You could use static gauge and do that. This is saying that however you define this tau, this integral over sigma is conserved. So then you could say, look, I don't know if this is the momentum or if this is conserved, and I want to use arbitrary tau lines. Well, what should I do? So you have your arbitrary tau lines that have nothing to do with time, and you compute this integral. You say, okay, I got something that is conserved on this worldsheet. Is it the right momentum? Well, it is, because suppose here the lines are not time lines, but then you have reparameterization invariance, and little by little you adjust them, and suppose now here they are time lines. Well, conservation says that this integral is independent of the tau you use. So you used one here that had nothing to do with time, but this one has to do with time, and they are the same. So this one is the same as this one, which is the momentum, and it's conserved in time. So you still get it. You can play with this more. The only way to make it really beautiful mathematically is to describe the whole integration to produce the charge as an integration over an arbitrary line on the worldsheet, not just over sigma, but you can use an arbitrary line, any line, and you can compute that integral. I will not get into that discussion because it's an aside, but people in general relativity also discuss it. They say, oh, you can integrate over all of space, but you can also integrate over a space-like hypersurface and find your charges, and it makes no difference. This is the baby version of this problem in 2 dimensions. It's the place where you can understand it best. So if you're interested, read about it. I wrote it in the book, and you can discuss what you're supposed to integrate in order to use arbitrary lines. But it will not be too important for us at this moment. So this really means P mu is conserved. And it is what we call the momentum of the string. And you should remember that formula. You obtain it as a conserved charge as integral over sigma of P mu tau. That's the take-home message after this. There's one more symmetry that we need to be concerned. Is Lorentz invariance. And this is the symmetry that we really put in from the beginning into the theory. And we say, well, this theory is invariant under Lorentz transformation of the x's. So how do we derive a conserved thing associated with it? The formulas for Lorentz transformation are so complicated in general, gamma, beta, and that's just for a boost. A general one is a mess. So how do we do that? Well, Lorentz transformations are complicated in general, but infinitesimal Lorentz transformations are very simple. Infinitesimal transformations are the simplest thing in the world. So, and here you need, basically what you're doing here is doing infinitesimal transformations. I maybe didn't emphasize that enough, but these epsilons are supposed to be infinitesimal parameters. If the infinitesimal symmetry exists, you can prove the large symmetry exists, but infinitesimal is all you need to check. When you check gauge invariance in a Lagrangian for the standard model, many times, or for many terms, you just check gauge transformations under an infinitesimal parameter, and when you're pretty strong, you change gauge transformations for a large parameter. You use a group element or a little infinitesimal element, and it's your choice which you use. So here, for Lorentz symmetry, let's try to understand what is an infinitesimal Lorentz transformation. So it's a variation of the x's, which is linear, is proportional to the x's. So must be some constant, epsilon mu nu, times x nu. And I don't know what that constant is, and probably it depends on which transformation you do, and let's hope that this does it. What is a Lorentz transformation? Something that leaves the quadratic form invariant. So what is this variation? Well, you have to vary this x mu and that x mu, but that you know by now it's 2 terms, so this would be eta mu nu delta x mu times x nu equal to 0. There's 2 terms there still, but and this is eta mu nu epsilon mu, and I shouldn't put nu there because that's another index, so I should put a rho x rho times x nu must be 0, and I can use the eta to lower the x index, so we have epsilon mu rho x mu equals 0. So what does that tell us? You have epsilon times 2x's equals 0. what that tells you is that epsilon must be antisymmetric. If it had a symmetric part, it would not vanish. Anything symmetric, epsilon 1, 1. If it's non-zero, you have x1, x1. So this must be 0 for all x, for any value of x. So the only answer to this is epsilon antisymmetric. So epsilon mu nu equal minus epsilon nu mu. So with this condition, delta x mu equal epsilon mu nu x nu is a Lorentz transformation. And that's why I told you it's the simplest thing in the world. Just an epsilon, an antisymmetric matrix defines a Lorentz transformation. And therefore, an antisymmetric 4x4 matrix has 6 parameters. Have to do 3 with boosts, 3 with rotations, and that's it. Now, you can take a boost, and it will not look like, and you can read what epsilon mu nu is. It's a good exercise to check that you know what you're talking about. And just do it. You will see it's simple. It's an infinitesimal Lorentz transformation, so you will have to assume beta is small and just expand it and see what you get. But now we have more conserved currents. So what are these? We have conserved currents associated with this many parameters. So I have J alphas, and I have mu nu are the indices. You see, just like how we got here a lot of conserved charges, each component of the momentum is conserved, supposing you have the right boundary condition. Here we're going to get a lot of charges, so we have in our formula epsilon mu nu times this. This is our top formula there. So this should be dl, d alpha x mu times delta x mu, which is epsilon mu nu x nu. Now, since this is antisymmetric, any symmetric part here would vanish by contraction with this. So there's really only currents that are antisymmetric. So I'm going to write this. Maybe, how did I write it? I wrote it that way, yep. Here, I'll just write that this is P mu alpha, because alpha can be tau or sigma. Epsilon mu nu x nu, which is minus epsilon mu nu. I put a minus there for convenience, and then I'll put x mu P nu alpha. That would be it. Is that right? Because epsilon mu nu is antisymmetric, so if I change the mu and the nu here, I get a minus sign. But I want to write this as a manifestly antisymmetric thing, so I'll put x nu P mu alpha, and I'll put a 1/2 here. That's still an equality. And at this moment you say, well, you know, I want to define my currents. If a current is conserved, 2 times the current is conserved, or minus 1/2 times the current is conserved. So I might as well define the current, calligraphic M alpha mu nu, to be x mu P nu alpha minus x nu P mu alpha. And these are the Lorentz currents, and they are conserved as well. Yes?
But, I mean, in general, you just, what it really does is that the antisymmetric part will get left in. I mean, you could add any symmetric part, and it still would be a current.
No, it would not be a current. It would drop out from here, and therefore you would have no reason to believe that whatever you add is going to be conserved. So suppose I put something symmetric, then I would have to invent something symmetric, and it would not be conserved. So at this moment, I multiply by this, and therefore I have this equation only defines the antisymmetric part. You see, if you have something like that, let me do a little example. Suppose you have 2 by 2 matrices. You have epsilon mu nu, j mu nu. Then you say, this is epsilon 1, 1, but that's 0. So that's epsilon 1, 2, j 1, 2, plus epsilon 2, 1, j 2, 1. Then you go on and say epsilon 1, 2, and this is minus that. So this is j 1, 2 minus j 2, 1. So your equation like that only defines for you this thing. And the rest, well, you know, there's nothing else that the equation tells you. So there's no symmetric part that you could add at this moment. It's only the antisymmetric part. Other questions? That's very important. Make sure we're okay with that. So another conserved thing. So what are the Lorentz charges? There are m mu nu. So just using the notation, we have calligraphic things for currents and capital things for charges. This would be the integral over sigma of m mu nu 0, the time component of it, of tau and sigma. And therefore, it would be the integral of x mu p nu tau minus x nu p mu tau, this sigma. And notice, of course, because we put the 0, these things became taus. So this is what you expect. These Lorentz charges are coordinates times momenta. P tau is momenta density, integrated over the world sheet. There is certainly, this includes rotations. When mu and nu are I and j, you're having x times honest p, not energy. If these things are spatial indices, these are momenta, not energies. If this would be time indices, you have the boost. The conserved charges associated to boosts are less familiar. You can read in the book about them. They're very seldom used. The angular momentum, however, when these are spatial indices, these are x times true momenta, so these are angular momenta. So Mij are angular momenta. Mij are what one would call, I think, 1/2 epsilon ijk Lk, where Lk is angular momenta. So M12 would be, no, probably, is there, no, there's no 1/2, I'm sorry, I think it's just like that. M12 would be epsilon 1, 2, 3, so it's L3 or J3. Let me call it J for angular momenta. J3. So we can do an exercise that I will just tell you what happens with it. If you have our rotating string of last lecture, remember it was a L over 2, L over 2. It was rotating in the x1, x2 plane. It will have an angular momentum. And the angular momentum would be M12. So the angular momentum J is equal to M12. And can be calculated doing this integral, which is easier to do than what it looks like. There's also possibility to do it sort of what you would call physically. What would you call physically? It's a nice thing to do it. If you have the string like that, you know there's a rest mass here, T naught ds. So it has some component of momentum, which is the relativistic momentum, as you know, is the rest mass, m0, times the velocity divided by this factor. So you multiply this length times the angular velocity times the distance from here to here and integrate, and you can find the angular momentum of the string. Or you can do this integrals. This is a little faster maybe, but this is more intuitive. In any case, the answer is quite interesting. This gives you 1 over 2 pi t naught c times the energy squared. And in order to have sort of nice units, people divide this by h bar, because J has units of angular momentum, and it's 1 over 2 pi t0 h bar c times e squared, and this is the famous constant alpha prime of string theory. That's sort of how string theory began. This alpha prime has units of 1 over energy squared. It's of 1 over energy squared, because this has no units. And this was the origin of string theory. In a sense, this little calculation of the rotating relativistic string and its angular momentum got string theory started in the old times. And you say, why? What's so special? Well, angular momentum proportional to energy squared is absolutely unusual. It's something that people tried forever to get and couldn't get it. You see, there's a usual relation. If you have a rotating object, the angular momentum is I omega, moment of inertia times omega. The energy is equal 1/2 I omega squared. So omega goes like square root of energy, and J, therefore, goes like square root of energy. Any rigid object that rotates, its angular momentum goes like square root of energy. And people had observed that in particle physics resonances, you had this plot as the energy, or squared, the rest mass squared of mesons. They fell into trajectories. And the angular momentum was here, and here's angular momentum 1, 2, 3, and it fell into lines, so proportional to e squared, and it was just absolutely unclear how you could ever get a model that reproduced that. And this relativistic string is the only object that does that, because in a sense, the moment of inertia itself depends on the length, and the length depends on the energy, and as you put more and more energy, it's becoming longer and longer, and it does funny things. At the end of the day, it ends up with a very unusual thing. This law of linear dependence on resonances is quite accurate. It's fairly unbelievably accurate. You put a couple of mesons here, draw a line, try to see what the mass of the next one would be. Error of 2%, 3%, very small. Yes? Yeah, the string tension is determined by the value of alpha prime. So alpha prime is a measurable thing, and then you can get what the string tension is. And that's how people in the good old times, when people thought that this kind of string applies to QCD, they saw that the string tension is about 13 tons or 2 tons or 2 tons or something like that. It's a big number. Now, of course, we know that the string that corresponds to mesons is a little more sophisticated than that, but still the origin of this thing is quite good. And very unusual that you need a mechanical relativistic string to produce such kind of relation. Now, Just to mention a couple more things, once you take h bar equals c equal 1, alpha prime, all things have units of length or of mass. As Mark Weiss has told you many times in his course, this has units of 1 over mass squared, which is the same as units of length squared, and square root of alpha prime is called the string length. So when people talk about the string length, they're talking about the square root of alpha prime. Moreover, we had the Nambu-Goto action that had minus T naught over C. And by the time you put h bar and C equals to 1, T naught is 1 over 2 pi alpha prime. The C, forget it. H bar, forget all the C's and alpha prime. This becomes minus 1 over 2 pi alpha prime integral, the Nambu-Goto action. And that's sort of the way everybody writes it. By the time you don't have to do very specific calculations and you're willing to put h bar equals c equal 1, which we didn't do until today, that's the famous form of the Nambu-Goto action. So we now begin. Let's see if there's any questions. We can stop a few minutes. Yes. Let's see. One there first. Volume. Yes, it's much, much bigger. Basically, LS is the string length. So if you want to do nuclear physics, L length would be a femtometer, the size of a nucleon, the size of a nucleus, or the size of a particle, the Compton length of a particle. When you do string theory, you typically say that LS is comparable to the Planck length. Yeah. Question here. No, it's not angular momentum. So the question is, what if we're talking about boosts but not Lorentz transformations? So you would have the generators M0I here, and they would be products of sometimes time times, so suppose you are in the static gauge, you would have things like integral d sigma of time times p I tau, the I component of the density of momentum, minus x nu, which would be p x I times p 0 tau. So it's not angular momentum anymore. Are combinations of time times the total spatial momentum minus sort of center of mass quantities. That's why it's not too familiar. This is like a center of mass, center of energy, because this is energy density, P0. Tau, whenever you say P tau, you know this has to do with P mu. Are the densities for these quantities. You know, this formula should be, this should be automatic. The density of momentum is P tau along the string. So this is the energy density along the string, and this is the length. So this is a center of mass sort of thing, and times momentum. So basically, time times velocity is the position of the center of mass. It's some sort of identity of that type. It's not that fabulous. And it's not angular momentum, for sure. Okay, so now we go and do Lightcon stuff, and we'll derive our constraints covariantly. So we have to generalize. Our first order of business here is to generalize the static gauge. The static gauge is a little too rigid for us. So let's try to get a more general version of that static gauge. So other gauges. And here is the first gauge we're going to take. We're going to do n mu x mu of tau and sigma is equal to lambda tau. What is n mu? It's a vector that you choose. N mu is a vector, a constant vector. So certainly if n mu was equal to 1, 0, 0, 0, 0, 0, 0, this would be x0 is proportional to tau, and you're back to your static gauge. Now, we're going to let this vector be fairly arbitrary, but in fact, we're going to let it to be, it begins time-like, that's the static gauge, and we can rotate it until it becomes null. We won't take it to be space-like. That's far too much. If you would take it to be spatial, you already would not be setting somehow of some time equal to tau. So we'll take n to be a constant vector that is time-like or null even. At the limit is null. You know, it's a funny thing. It's a funny thing about physics that all the interesting thing happens at the edge of trouble. You know, you have a standard model. It's at the edge of being anomalous. You know, anomalies cancel because the multiplets are well arranged. Here, for this n mu equal 1, your time, and you'll get to the edge of trouble as you take n to be null. But that's the place that it becomes very interesting again. You can't go beyond null, but null is very nice. Okay, now this gauge, which is going to include the Lightcon gauge, assumes something. Remember, the coordinate x0 was free. It evolved in time. It was always free. P sigma was 0 for mu equals 0. You had to have it free. So there has to be an analogous condition here. And we're going to demand that in order to make this to work, that the components of P mu in n dot P are conserved. N again, dot P, this will involve some product of some momenta. Well, I want all of those to be conserved. So I want n dot P sigma to be 0 at sigma star, any sigma star. Remember from our equations over there, let's see here. A momentum is conserved if the corresponding P sigma is conserved. So dot it with n, and therefore the n dot P on that side would be equal to minus n dot P sigma over there. So if n dot P sigma is 0, these things are conserved. Now, I will then write this equation in a somewhat different way. I will specify what this constant is and write n dot x of tau and sigma is equal, it will look funny to you. Many things will look funny for a little while. A lot of constants here. A 2, practical for later reasons. The alpha prime that we obtained there, which we're going to use from now on instead of the tension. This is a constant, so we'll put it here. It's sort of useful to have an n here and an n there, so this is a useful thing. And here is your tau. So that's how it goes. Now, this thing has another advantage or disadvantage, is that tau has no units now, and sigma will have it with no units either. So tau and sigma now are going to become mathematical. We discussed that in the Nambu-Goto action, the units of tau and sigma didn't matter. So might as well forget about their units now. From now on, we won't carry them. Otherwise, you'll have exponential cosine of n sigma. Now we'll have cosine of n times sigma times square root of h bar c over, it's a mess. No units. So here comes the more interesting thing. Remember what we did before, and that's why we did a physical example, because these things, unless you do them before, they are a little unmotivated. How did we do the parameterization of the string? We chose the static gauge that told us time was related to tau, and then our second step was drawing lines of sigma in such a way that the energy density on the string was constant. Sigma as a function of sigma was a constant energy density. So we're going to do the same here. We're going to attempt to require that n dot p tau. See, when n was equal to 1, 0, 0, this was P0. Remember, there's a mu index here. So this P0, that was the energy density. P0 tau is the energy density. So here, we're going to require that this thing be a constant over the strings. The strings. So constant along sigma. If we had more time, we could just review again the argument that this can be done. I don't think it's interesting, and again, it would be a little bit of a review of things we've done, but in another language. But I'll take it that we can assume this can also be done. So then we want to parameterize the string. Parameterize the string from 0 to pi. So how do we do that? We're going to write it. I want to write this as an equation. This line, these words, I want to express it as an equation. Remember that we express this constant energy as an equation in the static gauge as well. So let's try to write it as an equation here. So if we want to parameterize the strings from 0 to pi, I will do the following. I'll do 0 to pi d sigma of n dot p tau. What is it? Now, this is supposed to be a constant over sigma. So one way of doing this integral is to say, look, it's a constant over sigma. So it's n dot p tau times pi, because you told me you want the strings from 0 to pi. On the other hand, since this is a constant over sigma, this is this. But on the other hand, remember, what are these integrals? These are the integrals of p tau over sigma, so these are the conserved momenta. So this is n dot p, which we said is conserved. So we get an equation that n dot p is this. So this equation at the end of the day is n dot p tau is equal to n dot p over pi. So these are the two conditions that are equivalent to all what we did before in the static gauge that took us some time to understand. We fixed tau, and we fixed the sigma parameterization by requiring that this constant divided by pi is this energy density along the strings. And then we have something good. Now, I'll use 2 more minutes. I want to do a little more. I want to tell you about the equation of motion and what does this imply. From the equation of motion, we have d mu tau d tau plus dp mu sigma d sigma. As you can imagine, I want to dot it with n because these are the things we've been looking at. So dd tau of n dot curly p tau plus dd sigma of n dot curly p sigma is equal to 0. Now, n dot p tau is just a number. So it doesn't depend on tau or anything. This is an absolute constant. This is a worldsheet constant. So this is 0. And therefore, n dot p sigma, its sigma derivative is 0. If its sigma derivative is 0, and it vanishes at the endpoint, it's 0 all over. Because its sigma derivative vanishes, and by the boundary condition is 0. So n dot p sigma is identically 0. So what do we get from this? N dot p sigma, the formula for p sigma was a little complicated, but let me just write it here. This equation, n dot p sigma, is 1 over 2 pi alpha prime, x dot x prime, and you had dd tau of x here, dd tau of x. So this, with the n vector, will be dd tau of n dot x minus x dot squared dd sigma of n dot x. And then there's the awful square root of the Nambu-Goto action. So we're trying to finally see what this gives. And look at it. We have lots of notation, but these 2 equations that we've boxed are the key things. N dot x is proportional to tau, no sigma derivative. This is analogous to tau, so this is 0. And this is a constant. N dot x is a constant, so there's tau here. And this whole thing must be 0. So what have we learned? We've learned that x dot x prime must be 0. It's our first result. X dot x prime is equal to 0. This is actually familiar. If you had, this is a funny thing, because now it's a covariant looking equation, Lorentz covariant looking equation so far. And it's because we've introduced this n vector that allowed us to do things a little more thoughtfully. If you look at it, it would be dx mu, dx0, d tau, dx0, d sigma, plus dx vector, d tau, dx vector, d sigma equals 0. And in your static gauge, x0 was proportional to tau. So this was a number, but this was 0. And then you had dx d tau, which was dt, dx d sigma equals 0. That was the orthogonality of the strings to the velocity. So our familiar equation for the static gauge has been recovered, but written now in a more covariant way. So this is the first consequence of this. Next time, we will show that, in fact, x dot squared plus x prime squared is equal to 0 as well. And between these two, you'll have that x dot plus minus x prime squared is equal to 0. This and that, and these are the Virasoro conditions now more covariantly expressed. And with those, we will be able to solve the strength in the light cone. So we'll continue tomorrow. See you then.